So this is an attempt try to help what we heard, like David talked about, to get education, the capability and skills to a bigger audience, not just the data scientists, but really opened up the education to even government regulators. Yeah. So feel free to ask questions because it's better to be interactive than finishing all my slides. So this is about data science education. And data science is a key element AI. And whatever we defined it, data work has been really underneath all the advances which we now put under the umbrella of AI. And you have three components: computer science, math stats, and domain knowledge. And machine learning is the frontier of both fields. And we want to do actually vertical data science. This is something, a term actually, it's suggested to me by my colleague from Columbia, Tian Zhang, when we used to have, I call my talk, 3 principles of data science: computability, stability, and predictability. And she came out with this great name, short and sweet, like machine learning people. It's really about truthful and coinciding with reality. And the vertical data science is the term we put in the paper with my former student, Kumbir. It's really a philosophy and conceptual framework for practicing data science responsibly with the documentation requirement. There's a lot of things you still have to make human judgment calls. Relating back to Stephanie's talk this morning, science is not completely reasoning, rational either. There's many human aspects to it, and we want to admit that and make it transparent. And it's really an attempt to provide a framework for producing trustworthy data-driven results and critically assessing the trustworthiness of data-driven results in the context domain, science and reality. So for the talk, I want to explain why the book became the book. It's really motivation replication crisis. And also the time actually data science initiative started, Mike played an important role. I was also part of the core team. And now we have a new CDS, a new college, headed by Jennifer Chase. So it's all kind of the same 10 years that I co-designed this Data Science 100 with many colleagues. And that's where I was also trying to work on this book for the last 10 years. And the second part will be on the book. And the third part, actually, a lot of the information you get from book can already do very well for a real problem, prostate cancer detection. So if you roll back the time 10 years, then we actually had this called replication crisis. But before that, actually that happened a lot in oncology. So this is a problem people still work on. Prostate cancer occurs like in a lifetime for men, about 12% of the time. And the current test is called PSA, based on a protein from a particular gene. And the AUC, which means the area under the curve, really gives 60%. It's very high false positive. And that leads to invasive biopsies. So can we do better? Just keep that in mind, because the whole book is trying to ground the book to problem solving, not just X and Y's. We do use that, but it's really trying to solve problems. And 10 years ago, actually, this article two articles got many attentions, exactly in oncology. The replication rate was deemed around 11 to 20%. It's by the people from these two companies. And you move forward, Nature had a paper, they did an online survey of 1,500 scientists. About 70% really expressed pretty serious worries about whether there's a replication crisis in science. You move forward, 2 years ago, there were 73 teams of independent researchers in social science, and they were vetted. They were not just people like Kaggle, anybody can do. They used the same data, test the same hypothesis about immigration and social policy support. And they got results, some very positive, some very negative. So this is a hidden universe uncertainty. And people in ecology, a year later, had over 100 teams of people work on 2 different data sets, but same. And they have a title, same data, different analysts, variation in effect size due to analytical decision in ecology, evolutionary biology, right? So this is scientists really sounding the alarm. This is not dealt with by traditional statistical or machine learning approach. So what we try to do is really help improve data science education and data science in general and practice. Good statistician data science are really detectives. We really have to really do the best we can and formulate the right problem with the data you have and use your domain knowledge, context, and relevant theory to collect evidence. We cannot just p-value, then we make the decision. So we really need to think as a whole ecosystem, human, decision-making, and impact. So now come the book. So this is why we developed virtual data science. And the book started 10 years ago. And online version already appeared in February. MIT Press has been very generous, allowed us to do that. And the paper version appeared in October. It's called Vertical Data Science, the Practice of Responsible Data Analysis and Decision Making. And the intended audience is actually upper division, beginning graduate students, and as a standalone book or go with a traditional book. And also domain scientists, including government officials, for them to learn on their own about data science. It's very accessible. And credit goes a lot to my co-author, my former student postdoc, now professor at the University of Utah, Rick Butter. So she does great blog and Twitter, and just check her out. So what's the goal of data science education? Right? You can choose A or B to prove mathematical results about data or to solve real domain problems. In some sense, we do both, but most people in our classes, they do B. And relevant theory can really help practice, but we have to check assumptions. But not all theory can afford to do that. So if you go by 1965, Marvin Zallen said that scientific inference from set of data is not the formal exercise one finds taught in statistical classrooms. Today, the way one draws an inference from a real data set is taught in many classrooms of statistics in exactly the same way as one would teach geometry or algebra. The student learns that statistical method consists of a body of formulas and fixed sets of rules, which once memorized can be used throughout one's lifetime in drawing inferences from data. So this is what recited by Steve Goodman, 2019. I think we have moved away, made progress on that, but still a lot of times statistics taught that way. Statistics use mathematics just like many other sciences. My personal view is not mathematics. And it should talk more like science. And with different views, like physics, they talk different theories, and that's what we should be moving towards. Pluralism. There are multiple explanations often about a particular data phenomenon. And we need to really show all of them instead of like math. Math is beautiful, elegant, but real world is messy, not uninteresting though. So the traditional textbook usually start with a data set. Very few books start with a problem. And we do some visualization, numerical summaries, and then we quickly assume a true model and start devising optimal mathematical solution. If there's a good model, yeah, optimal solution is great. But in my own practice as applied statistician for the many decades, I haven't seen a problem that I can say, this is like close to a true model. Usually, you have a goal to achieve. And model checking, the uncertainty is very limited under, if you have a good probability model, we know what to do. And very few books that will have really serious coding exercises. It's kind of taught separately. So there are gaps, right? In practice, the first thing you do if you have a master's student, PhD student working in industry, or even for your own research problem, you have a scientific problem or domain problem, you have data, and you don't have true model. Often people try many models and cherry pick, and then usually don't report other models. Maybe, I'm just guessing this is sociology, possibly to align with the true model framing, right? People, the books doesn't talk about multiple models. And there's a hidden problem in the whole pipeline is data cleaning. I didn't worry about it when I started writing the book, right? The more you think about it, the more data cleaning actually takes a huge, people do it 60%, 80% of your time, but we usually don't report it. We pretend it's not there. And different people clean the data different way. And you get different results, possibly. And coding, you cannot do data science without coding. But it's not usually an integral part of the textbook. So in our book, we try to do better in all three aspects. So first thing actually in the book, we don't talk about math or models. We talk about very conceptual discussions. Reality and real data are not the same thing. Often it's a reflection. Even you take a photo, it's not exactly the same thing. Two different cameras would get us different things. So reality, that's the first differentiation conception we make. Data is not reality. And there are many versions of reality shot, like photos. So we start with this graph. You have real world, and domain knowledge is always there. And we say data is approximation. Is that good approximation? So use this terminology, make people think, is that good approximation? Then you want to look at the data collection process. And models are not real until you connect with reality. They are mental constructs. You don't work on your data because you care about the data in hand. You have a future situation. You want to worry about that. And that's very important when you set what's the test set. You want to mimic the future instead of always do random split. And then you have decisions to make. It's not just because we have a p-value and we're done. You want to think about humans, the people, the decisions, your impact, and the future as much as you can. And we actually make many, many human judgment calls in the data science lifecycle. Right? For example, the human analyst, we have 6 right there. They make different calls. They even choose different data for the same problem. Data cleaning protocol already mentioned. With assumptions, right? People in causal inference, for example, for observational data, different people make different identifiability assumptions. And you might get different causal conclusions. That's also modeling choice. And even with the same assumption you make, you still have, if you assume a linear model, you could do least squares, you could do L1 panelized, you could do L2 panelized. So just so many judgment calls. It's really a whole forking process. And actually goes through a whole data science life cycle. Right? If you concentrate on this, let me ask a question. If suppose I'm coming out with diagnosis tool for prostate cancer, and I only tell you this part, are you going to trust me? So which one is going to give you more trust? That was also discussed in the panel. If I tell you only the modeling step, or I tell you every step? Who wants to go for every step? Who is happy just with this? Good, nobody. But if you go to conferences and papers, usually we only see that. For paper publication, we just come to a point that it gets published. But if you really put yourself in the shoes of a patient or the relative of a patient, you want to know the whole thing. And that's why we need to have the habit of reporting the whole thing. And first, starting from students. Right? Prostate cancer. Where did I get my data? Is it TSTIG or my own data from my collaborator? Who cleaned it? If I cleaned by a different person, will I get the same result? If I use lasso or elastic net, do I get different result? So all of these questions need to be addressed instead of put under the rug. So uncertainty quantification is something statistics, data science, machine learning people all care about. It's central to building trust in data science and AI. But right now, formally will only consider the uncertainty if you have a good stochastic model, the sample-to-sample variability. It's important you have a good model, that's probably adequate. But a lot of time, our stochastic models are not even empirically checked enough. We don't do a lot of model checking these days because it's hard. And in data science life cycle, there are many, many other sources of uncertainty due to human judgment calls, and we want to go for trustworthy uncertainty quantification. Uncertainty quantification is great, but I think we also have to ask, do you trust uncertainty quantification? For the large language model, they give you uncertainty quantification, but it's not trustworthy. So I usually don't want to give uncertainty quantification unless I know I can trust it. Sometimes it can be misleading because people might trust too much. And scientists already start taking into account this multiple team effect, right? This is 1991, the IPCC report. And we try to predict the global temperature in 100 years. You don't see one curve. This is not confidence intervals. This is from 9 different teams, leading teams, doing the prediction from 1.5 degrees to 5 degrees. They use similar physics, but they did something just a little differently, and they get different results. And it's healthy for us to see the whole range than just take one, think that's going to be a prediction. In the absence of not knowing exactly to do the traditional quantification, what's the stochastic model, this is a right step to give us some very pragmatic uncertainty quantification. So that's what VDS or PCS will try to take advantage to in a similar way. So I think in a house of uncertainty, we have 2 big elephants we're not taking care of. I hope to remove them. One is from data cleaning. One is from the different choices model by different teams. But because of availability of software, one team can actually try multiple models much more easily than 30 years ago. So we can all address this uncertainty from team effect, even by one team. So again, back to reverse data science. It's a practice extracting reliable, reproducible, realistic information from data. That's a tall order, while recognizing that this information is a function of the judgment calls made throughout the entire data science lifecycle. And assessing critically the impact of these judgment calls on the conclusions made in the context of a domain problem. So this framework is purposely kind of philosophical, conceptual, because what's a reasonable judgment call? I cannot tell you unless I know the context, right? You have different perturbations. And I'm just saying that if I drop my phone here, it shouldn't break. But go to the top of the building, I drop it, that's an unreasonable perturbation to my phone. I cannot sue Apple for it because you're asking too much. It's not reasonable for the context. So the context is important to know what's the reasonable perturbation. And to practice reversible data science, it's really through these 3 principles of predictability taken from machine learning and statistics, and computability and data-inspired simulations, and also expanded consideration of like uncertainty or stability from sample-to-sample variability to data perturbation through data cleaning, different forms of bootstrap, and also different choices of algorithm. So it's a huge expansion, try to unify and synthesize a lot of work I think people are already doing in good groups and good labs. And intend to unify and expand on ideas and best practices from machine learning and statistics. So let me just expand a bit more on predictability. So when we first developed this, it's an evolving framework. I was only thinking about predictability as in machine learning sense, but now the P has evolved as a stand-in for reality check. For transfer learning, often you don't really have predictability, but you have domain knowledge. So P, because I'm stuck with PCS, it's really about reality check, beyond prediction. So the minimums are if you have good scientific theory, does it generate good prediction? If it doesn't, probably you're not capturing reality. And you want to see the result re-emergence in new or future data, or by a different alteration of your data, right? So the first work we did along the PCS deadline was the work with my former student Chim and Lim at National University of Singapore, was really try to build stability into lasso, like regularization parameter selection. So that inkling came, I was working with Jacob Lam, my neuroscience collaborator, and they collected data. It was like image and fMRI observation. For some reason, the student collected an hour and 15 minutes. It's kind of odd, because I would say maybe it was 2 hours, wouldn't have raised the concern. I said, well, what if I just do an hour and 40 minutes? So I deleted 10% of data, and the two actually give very different selections. Right, that's actually the beginning of this framework, was that neuroscience project. I just thought 1 hour, 50 minutes was odd. And then we struggled to know how to introduce stability. We didn't know we needed predictability. And Ching Wei was such a good sport to just go with me, and many false starts. And we had stability-driven cross-validation. It took like 12 months, if not longer. Looking back, that actually had a lot of all the ingredients of the framework. I didn't see it, and I didn't worry about all the things now. I said, now we should all worry about it. I was worried about modeling myself. I realized stability is such a broad concept and principle. Even for linguistic stability, is very important too. Right? We have different people from different disciplines, and the acronyms might not mean the same thing, right? When Xiaoli and I were in graduate school, what did ML mean to you?
Maximum likelihood.
Exactly. We thought ML was maximum likelihood. At a certain point, we all conformed. ML now, to me, is also machine learning. So even linguistic stability is needed. So stability is just really overarching. And you want to make sure that your algorithm uncover known expected relationships. And that's kind of predictability, and qualitatively and also quantitatively. And computability, of course, is a given in today's world. You create and use data in an efficient way, but we add under C, under PCS, data-inspired simulation. So we wrote a recent paper called Marriage, try to synthesize the good data simulation practices so that we have more standardization. And you want computation efficient, and the computation available through the right interface for the user you want to communicate with, and do data-inspired simulations. Stability is, I think, the major contribution PCS on top of machine learning is really expanding the statistical uncertainty to the other source of uncertainties. You can make other judgment calls. You could choose a different problem, and you can perturb your data in many different ways reasonably. And all of this doesn't remove human judgment calls. It just makes us more transparent. So we need to document, and document through R Markdown or Koto or Jupyter Notebook. And documentation also makes you a better critical thinker to evaluate how you think. And also for the next lab mate or the future collaborators or future yourself to know what you did. And now in my group, in my class, it's required people just do documentation. And you don't get to publish all that, but it's as a supplement material. And data science reproducibility, from the stability angle, reproducibility is a special case of stability. Right? Replication, you can also say, is a special case stability from lab to lab. And data science reproducibility is more like computational reproducibility, is that somebody else independently replicate, reprogram up, recode up, get the same results. Of course, you have to agree on the modeling, otherwise you don't. And the other is that you redo yourself. The third is that somebody read your code and vet your code. So there's different levels of reproducibility. And it's a form of stability. Stability is very, very broad the way I'm advocating it. You define the reasonable perturbation, you define a performance metric or multiple performance metrics, and you evaluate it. So in project we did for COVID death prediction 2020 actually appeared in HDSR, that we use 3 different metrics. One is the absolute death count difference from the prediction and observed. The other is relative. The third is take a square root of the death count because long tail, because in our modeling we use a square root. So we want all 3 metrics to be good for a particular model. So back is that we intend to build trust in data result by being transparent, document, and perturb the system in a reasonable way and ensure that we have enough stability. Stability is kind of analysis. It's a easier way to do uncertainty quantification without the quantitative judgment, like quantitative, I would say assessment like 95%, and it's when you do many ones, if you do each, you do 100, it just explodes. But this allows you to do less, but still get a good handle on the magnitude of the perturbation resulting in your final result. So back to this documentation mantra, it's a mental construct. Is there a bridge there? You reckon it's Golden Gate? There's a fog. It might not be there. Maybe it's once built. It hasn't finished it. So you have to be responsible to use quantitative and qualitative narratives and code to make the link. So PCS is really intended to be like bringing a lot of liberal arts type of thinking, qualitative thinking, into the quantitative discussion and do it together. Because you cannot solve the problem of reality and symbols by proving more theorems. You have to use narratives. And that's what you intend to do. And we have a template you can use at my website. You can just take our template and put your problems, especially for beginners. It's really helpful to help them streamline their plans and for data analysis. So now you have heard a little about veridical science. I want to re-articulate what we mean by veridical. Right, this is also evolution process for myself. I like the word, used it. Veridical means truthful in English, and it's a common word in Spanish where it implies a bit like verified truth, so that's a tall order. So practically, it really means we try to seek truth in data conclusions, and we also want to be truthful, reporting the process. So it's both about the process and about the goal. So as I mentioned, this is the book, and we are now going to open the book and show you a bit what's inside. So this is the online version. Again, thanks to MIT Press for being generous. Let us have this version 8 months before the paper, real physical book comes out in October. So the book on the online version, you can see we first talk about concept, the life data science life cycle, the philosophy, and then we have a whole chapter that a lot of people love. It's actually the preparation of data. It's preparing, exploring, and describing data. And then we basically go to so-called unsupervised learning with principal component analysis and clustering. Even in the original paper, we only talked about supervised learning. Here, actually, you can do both. And then we go to prediction, and then last chapter, 13, is with quantification, regression prediction intervals. And we don't do deep learning, but we do, oops, that's bad. Yeah. I need to go. We do have a chapter on decision trees and random forests. If you opened up the clustering chapter, right, you see, oops, I'm not good at using this, mixing up the pointer. And then you see the subtitles. We cover the standard, but all of this through a case study. So we talk about going through these different standard methods in the context of analyzing a data set. And then we have exercises I'll tell you about. So the goal of the book with this content list is to help students to learn how to ask insightful data-driven questions, how to think critically about data in the context of the question being asked, how to clean and formulate your data, how to structure analysis. We have to choose a computing platform, have to go through the different steps about missing values, and how to scrutinize. So every chapter has a PCS scrutinization, looking at the PCS angle on all the results and compare different methods. And we do cover commonly used statistical machine learning algorithms. So how does it differ from a typical book? As I said, we try to mirror the practice and follow the data science life cycle. And we have a chapter on problem formulation, data preparation, and about communication, because you have to do PCS documentation for all the case studies. And we use the PCS overlay and the documentation and try to be comprehensive and coaches critical thinking. And also just say that that's what we keep saying, that this is our decision, our judgment call. That's how we're going to analyze the data. To say that you might think differently. And it's highly recommended that if you want to use the book, you can replace the case studies I'll mention with the case study you know better about. We chose case studies kind of with more common knowledge. We have an organ donor donation data set. Rebecca worked on her thesis. We have some housing data. We have some nutrition data, just try to see that people can relate to. But if you have better examples, you can completely relate and use your own. And detailed differences, we definitely move away from the true model framing. We start with the problem. We start saying you have all these choices you have to make. We try to say that when you can use this method and why. And we use case studies, standard methods, and we add 2 new sources of uncertainty, as I mentioned, data cleaning, the 2 big elephants, and the models. And we have 5 kinds of exercises to really help to bring home the messages and give them some practice. So it's true and false, conceptual, mathematical, coding, and project. So we emphasize about the data split. It's more like talking from machine learning. And say that you want your test data to be the best proxy as possible to your future situation. Right, so we talk about at least three kinds of splits. The first is the random. You think everything's symmetric, the future is exchangeable. The second is used a lot in medical. You have different hospitals in your data. You want to set hospitals aside, not to scramble up and do random selection. And if the future is the prediction, you want to do time-based split. So you want to predict the future. So we have examples in the book on all 3. So the context dictates which is the better split. The guiding principle is that you want the test to be the best proxy possible for the future. So that's why you need to introduce the future very early on, instead of it's all about the data you have. Now it's clear that people are going to say, I'm going to take a different hospital as the test set, because I know the algorithm I want it to be used to a different hospital. Unless you know that the algorithm will only be used in UCSF, and maybe you want to do a random split. So again, help you to think about who's going to use the algorithm. And the case studies and project exercises, as I said, we have 3 data sets. We want the students to feel like they know something about the case studies. And that's why we chose this note from our research project. When I teach the class, usually I take from my research project because I have more time to explain. And also, it's a graduate level class. And when I use the book, actually I do more math than in the book. So I use David Friedman's book to go with it, and also with the statistical learning book. So this is try to not to duplicate too much what great books have already, and try to complement it. And all the codes and data available. And so you can really replicate, try to write up your own code and compare. So it's meant to be self-study. And if you look at another chapter, on data preparation. Then we have these steps in boxes to help you to organize things, right? You look at, I want you to learn about data collection. Then we talk about how do you get the background domain. We talk about talk to people in your network, look at Wikipedia, go to libraries. So we talk about all these issues, how to try to get that domain knowledge, and how do you load the data, and you create all these different action items. What's a valid value? What's a missing value? We advocate for simple missing value imputation instead of using heavy models, because then you have modeling there already. And what's the data format? Make sure your column names are there. What's the variable type? Incomplete data. So all of that is very much step by step. And we said you might end up, we recommend you end up with multiple copies of data. Unless you say that's only the right way. It's fine, you write about that. Most people say, yeah, I could have done the other way. And this is just an example from true and false exercise, just cropped it, right? You can see that data cleaning is an optional part. Just help them to think about this more clearly through the true and false questions. And pre-processed data can contain missing values, right? Just things like that. Just help them, force them to be sharp. And we also have conceptual exercise. Do some simple plotting and ask some simple questions about the data. So this is also encouraging them to look at the data through the exercise, not just go to programming up. And back to chapter on clustering. Then we have a section on scrutinization of clustering results. You have 3 k-means. You end up with different local minimum. So you do 3, 4 random initializations to get similar results about the silhouette score. This is a measure about how good the clustering is. So basically goes through the PCS pipeline to through the analysis. And then you have mathematical exercises. And you have coding exercises. You write some code. This is for R, not for Python, but I'm sure you can translate with the ChatGPT. Actually, people say it's pretty good translating. And project is like small labs that you basically want them to do some open-ended data analysis. And we purposely have boxes, as I mentioned earlier, to emphasize, so people can skim through and what's the important part, and this is a whole box about stability. So for the last few minutes, I want to go back, all the things we have in the book, actually you can already do frontier research, more or less. So back to this prostate cancer detection. I started working with MD Anderson Cancer Center because I gave a talk 5 years ago at Hutch. Ziding Feng, who's the validation center director, was very frustrated that the replication rate of biomarkers was less than 10%. So he thought this could be helpful, but he said, I have to work with a cancer researcher before they will start being open about it. So we already have good study with prostate cancer with Sam Hanash's group. And then I was invited to give a keynote in the Early Cancer Detection Network of NCI last September. And about a year ago, I went to Ziding. I said, I want to go in with more than one case study. So he introduced us to Ru, who's a cancer researcher from Michigan, and my 2 former members, Tiffany and Anna. At UC Irvine, and she's going to Notre Dame. So they already have a paper called MyScore 2.0. They had paper on ICAP, so we said we want to stress test your result, basically redo the analysis. And they were generous to let us do that. So the data they used was cancer data with clinical variables and 54 genes. And they have already lined up external studies from Hutchinson. And they want to predict more serious clinical significant prostate cancer, grade group 2 or higher. So that's a typical prediction problem. And they end up using logistic regression, a logistically elliptic net, with 17 genes plus this KLK gene, which is the protein that produces a protein in the current PSA test. And they got really good result, right? So what's being used here is about 60% AUC. They could go to 80%. But they had some earlier works go to 70-some%. This is all from the same group. So they increase So it's a huge jump. If you can jump from 60 to 780. So how to read this for people not used to it? This is basically, you want to be here. You want to have, everybody says it's positive, it's real positive. Anybody you say negative is negative. So you want your curve to be as close to this point as possible. So this direction, the better. Okay? So you can see that the current one is here. And this is the two new ones are right there. So it's quite a big difference. And then we talked to Yuping Zhang, who is the data analyst, saying about the data processing step. Say, could you have done something different? She said, yeah, I could have done something different. So we tried three more ways. I won't give you the details to see how much variability they'll bring. And then we did prediction check, and then we did a stable ranking of genes. We have basically decided there are many good models based on prediction, and we should rank them according to different models and do an average ranking. And we look at the subgroup accuracies. So what happened is that we have 4 different ways of clean the data with blessing from Yuping. The original one means the base, what she did, and we have 2 other ways, some thresholding. I won't have time. So you can see that this method, which is logistic elastic net, pretty stable. And this is the second 4 different cleaning method, another method, and so on and so forth. And we said this is just seemed to be worse, and we cut it here, so we took the top 5 methods. But then the uncertainty introduced by the data cleaning for this group is actually pretty small, 1 to 2%. I did the exercise in my class, there was like 10%. So this is a very good group. They kind of know how they want to process data in this game and small data. So they're pretty good. It's kind of standardized, close to standardized. So we removed the last 3. You could have cut here too, but we removed 3. And the rest we call the predict checked models. So among these 5 models which pass the prediction check, remember PCS, C is always there, and S, each method has a way of importance ranking. And we took the ranking and we did the average. We took the top many. We ended up talking with 7. So we end up with 7 genes plus the one. This one has to be there. That's the experts want it to be there because they think it's very related to prostate cancer. All the ones we found, we start with 54. They end up with 18. They couldn't go down anymore because ElasNet wouldn't allow them. But we could go down because we use different methods, and that's really helpful to get diverse opinions. And all of them are known cancer genes. And we get very similar external validation results from the 18 gene. So this is really good news. And we lose about 1 to 2%, but remember the data cleaning really introduced 1 to 2%. So it's really comparable if you take into account the data cleaning uncertainty. And then Aru actually had patent on MSP, MPS2. So he wants to go for this one now because fewer genes, and we became co-inventors. So this is declaration of a conflict of interest, and Berkeley is the joint intellectual inventor of this model. So people ask me, what's the secret sauce of VDS or PCS? It's really good data science hygiene, critical thinking, assessment uncertainty reasonably, and documentation. But there's one more thing beside the hygiene. It's actually uses very simple common sense. When you go to a doctor, you don't want one opinion. You want multiple opinions. This is exactly what we try to do. But you want good doctors. You don't want to go bunch of doctors and get noise. So you basically use prediction to find out good models, and you integrate. And that's really the other secret sauce. So again, the book is online, and check it out, send me comments. And as Xiaoli mentioned, they already have like an ad for our book, review of the book. And Xiaoli has been really supportive of the whole enterprise. And even before the book was in the final shape, has showed a lot of interest, and I really appreciate that. And thank you very much.
Thank you very much, Ben. Let's take some questions. David.
Ben, that's lovely. I think it would be very hard to communicate the importance of this protocol to a student unless they've seen how badly it's done in practice for a few years first.
Actually,
Good point.
you'll be surprised. So I ran assignment for responsible AI for like 5, 7 undergrad students. They definitely had no problem. Most of them haven't taken any statistics classes. I think it's a lot of common sense and trust. They have to trust the instructor.
Well, thank you, Professor Yu. That's really a great talk. A lot of great ideas about the VDS, education, problem solving, and especially solve real world problem. I have one specific question on the validation part. I'm a statistician from industry, and we submit analysis results report to regulators. And often we need to submit the program code as well. And some regulators even write program to validate. I just recently have a conversation of regulator, policymaker about the AI ML impact. As how you're going to validate the ML results. Are you going to write code? Are you going to read the code? Let's say it's not really feasible any longer, especially ML method data-driven. It's hard to imagine to replicate the result. So what's his suggestion you can give to the regulators to validate machine learning algorithm results in processing the data and analyze the results when it's become less and less feasible to try the traditional code validation or recoding any longer? Thank you.
That's a great question. I think if the codes are now secret, they can use citizen vetting. So a lot of our code put on GitHub, and we have co-authors we never met because they helped us with our code. And then there's also a journal called Journal of Open Source Software, and basically the reviewer basically vet your code. So you can consider sending the paper to JOSS. That's for software. It's not like 4 pages about, but it's basically the reviewers are the code reviewers. And in my group, we're starting to do that, not great yet, but we want all the code written by a subgroup of people vetted by somebody else. And if it's not working, then this person become a co-author of the paper. So we have done that with somebody else from a biostat. We have a package called SimChef, and the biostat student just started working so much, and he ended up being a co-author. But I think FDA should start having code vetting groups inside the FDA. That's a good money spent. If you think they cannot use, I think they should probably have that to vet the code. Just like they have statistical review panels, right? I think they should start have software engineers inside the FDA.
Thank you.
Yeah.
Thank you so much for the insightful talk. That really clarifies many things that confused me in the past. I want to ask a question about how assumptions underlying many inferences fit into your framework. Let me sharpen this question. So when we make prediction or inference, we often do it under a number of assumptions. This is so in causal inference and also the case in many other problem contexts. So I wonder whether those assumptions are part of the real world context of the domain problem, or are they something to be perturbed in your PCS evaluations because those assumptions are also human judgment calls, or maybe they are both or either, or maybe some assumptions go into the context, some assumptions are to be perturbed. I'm really curious how assumptions fit into your framework. Thank you.
So I think these are very tough questions. But I think assumptions depends on what you do with assumptions. So when I teach these squares, I try to teach it as an algorithm, not as a linear model. Because as an algorithm, you can value for prediction. But when you have all the other structure information, it depends on how far you want to go with your conclusion. If you only use so-called linear model to do prediction, and you just need prediction validation. And the assumption about linearity, even structure, additivity, all that are not as important. You just compare how good you do prediction. But you can take a p-value out. And that things get very serious. So there, my suggestion is that you should fit your data to multiple models, good modeling of data. That's something we try to write up. But it's not easy to what's good enough to simulate from and to understand the properties. I know people in causal inference for observation study already start doing ensemble of causal effect estimation from different identifiability assumptions. So I'm having this discussion with a Stanford colleague about that. So my thought is that also depends on what you're going to use that for. That kind of take care of the human judgment calls. I would like to see you write a document, which doesn't appear in a lot of causal inference papers, about why you think you can make the identifiability assumption. That's going to be hugely important. And your research record making such calls in previous study also matter to me, your reputation as a scholar. So it cannot be just contained in a paper anymore. I have to look at you as a scholar because those are qualitative calls. And I mostly follow the like Neyman Rubin framework, but when you go to instrumental variables, things like that, I usually don't go there because I couldn't convince myself anybody's assumption. I don't have the context. I find it convincing for me. And I talk to some researchers who do that. They don't disagree with me that it's hard to make the call what's a good instrumental variable to introduce. Very few cases people actually agree that's a good call. So that's something I think documentation will help. When we start writing things out more in detail, then we're making progress just to see what are the arguments we find collectively convincing to make a particular identifiability assumption.
Thank you, Bing.
Yeah.
Let's take one more question, then we do need to take a break.
Thank you. Love this talk. And to me, it seems like this is perhaps the most formal structured study of data science life cycle. And you know, like for data science, from the beginning of getting data to the finalize the model, it's a long process. So as you mentioned, at each step, you have many, many choices. Like even for taking care of missing data, you have 10 choices. So multiple together, you probably have hundreds of paths. And so I'm wondering, and you mentioned that you have like want to assess the impact of each human decision. And I'm wondering if you have any framework for doing that.
Yeah.
And the second is that you have very good concept about stability. And what do you mean by stability? How do you measure that?
Yeah, good questions. So the first is that I have a slide I didn't show here. It's like, if you do all the possibilities, you never go home. You never finish. Right. So you still have to make a meta judgment call. With the human resource, computing resource you have, we also have software to help you do stability analysis. And it's like, what's at the pain point? You have to make a judgment. We mostly now doing only marginal perturbations, not combinatorial perturbations. So we have one step, we maybe do twice. So at least start with 2 clean copies of your data and do marginal perturbation for you to think the important step. That's a start. And it's really constrained by energy and resource. Your second question is, remind me.
How do you measure stability?
Right. Stability is defined as, you first say what's a reasonable perturbation. And then you define the metric to measure the change in the result you care about. So, and you write a document about it. So it's very broad. Give the user a lot of freedom, but at the same time, documentation helps them, make them think more carefully. The good thing about this PCS is that with all the paper publication pressure, people will not want to do a lot. So in that sense, I just want people to do some. People are not going to just doing everything, because the direction of the wind is blowing people want to publish more. So hopefully do at least something, slow down a little bit. So I'm not really worried about people actually end up doing everything. We're not there yet. Maybe one day that'll be a good problem to discuss. Right now, people don't do enough.